Second question 16108, it says that a rod is confined to move along the path due to the pins at its ends. At this instant shown, point A has the motion shown. Determine the velocity and acceleration of point B. So we are given with the motion of point A, where the velocity is 6 feet per second and towards the right direction, and acceleration is towards left, and it is at 3 feet per second square, and we have to find it at B. And as we can see, it is a semicircle over here, and then the pathway, and this is the rod, and it is of 5 feet in length, and the radius of this semicircle or the curvature line is 3 feet. So we have to find two unknowns, and we are given with two things: one, velocity and acceleration, and also the length of AB rod. And first of all, we have to find the velocity. So for velocity, we use the equation VB is equal to VA plus omega multiplied by R, B respect to A, relative to A. So we have the velocity of A, and we have to find the velocity of B, so we can use the respective thing. So in this, we know that VB is moving in a vertical direction, as you can see from the path over here, and A is moving in a horizontal direction. So VB has the component J in it, and the velocity of A, which is 6, it is 6i because it is moving towards right, which is a positive direction we assume at the start. And omega has a direction K, and we multiply it by R, where we have to find it B relative to A. So we are coming from A downwards and then towards left towards B. So we can draw this triangle over here. As we can see that this is the rod, which is of 5 feet, and also we can see that the distance from A to B vertically is actually the radius, because the radius from the center point of the semicircle is always equal. So the vertical distance is 3, and by the Pythagoras theorem we are able to find that this is 4. So 4 is the horizontal component and 3 is the vertical component, so both have negative sign as it is coming downwards and towards left. And we further just simplify it, like K multiplied by I is J, but there is a negative sign, so there is negative over here, and K multiplied by minus J is I, because without minus it's minus I, so that minus cuts. So we get the final equation in form of VBJ is equal to 6i minus 4 omega j plus 3 omega j. So we have omega, which is unknown right now, and then we just compare the both I and J components. So we are able to find that there is 0i over here because VB only have a direction in J, and we are able to find omega is minus 2 radian per second. This minus 2 shows that it's moving in a clockwise direction, and we just substitute this value into over here in the J components, and we get that VB is 8 meter per second. It shows that VB is moving vertically upwards. So we are able to find one missing thing. Now we have to find the acceleration at B. So we use the formula AB is equal to acceleration at A, and then this is similar the relative thing. So this is alpha multiplied by R, which is P relative to A minus omega square R, and which is P relative to A, and then we simply put in the values, and in this we can see that it is moving in a curvature, and the acceleration is divided into two components. One is the normal and one is the tangential. So we just break the acceleration at B into two things. As you know that at A it's moving in a line, so you don't have to use the component thing, but over here it is moving in a circular direction, so that's why we have to break it down into two components. And then acceleration at A is minus 3i because it's towards left and it's given in the question, and then alpha, which is k, we don't know the direction or any value, and then minus 4i minus 3j from the previous triangle we formed, and omega is minus 2, we found it previously, and R, which is P relative to A. Now as you know that there's a formula for the normal component of acceleration, which is v square over this P, and we know that this is actually the radius of the curvature, and we know that which is 3, and we know that it's 8 from the previous finding, and the tangential we don't know, so it stays as it is. And then we just simplify the equation on this side, where k multiplied by I is j, and there's a negative, so negative come here, and k multiplied by j is I, negative I, and the negative cuts over here, and then we just simplify it by adding the j and I components, and then finally we compare both of the components, and we get that alpha is 25.9, and it is positive, which shows that the angular acceleration of the rod is in counterclockwise direction. And then we are able to also find the tangential component of acceleration at B, which is 0.889 feet per second square. And then we have two acceleration components now, and we have to find the magnitude. We just take the square of both components and take the sum of them, and then use the square root, and we get the acceleration, which is 21.4 feet per second square. So this is the magnitude we have gotten. Now there's direction to it as well, so to find the direction we divide the tangential divided by the normal direction, and we get that it is 2.39 degrees, and over here we can see the direction. And also if we go back to the diagram as well, so the acceleration has to be on this side. So it's, if we draw mathematical trigonometric quadrant, so it is in the first quadrant. So this is the acceleration at B, which is 21.4 feet per second square with the angle of 2.39 degrees. So if we just need to find the magnitude, we wouldn't have to break the components over here, but for finding the angle we had to do that.